All right, let's get started. You're literally the last remaining surviving soldiers of today's weather. As I checked, the campus is still open, so we start the course. All right, so this is going to be the first section of this, your second part of the course. We start by clustering, so we shift our focus to unsupervised learning from supervised learning, and then so we start with clustering, and then the next section we're going to have density estimations and other techniques that are related to unsupervised learning. So let's just have a recap for the unsupervised learning. So what we have here is a set of data in a vector space. So we have x1 up to xn, and all those xi's are in d-dimensional space of R. So we call them capital D as our data set. And as you recall, for the unsupervised learning, we have no labels for this data. So we are trying to find a way to gain some information about this data that we don't have any labels. So if you remember in the past, if you had several types of coins and you knew what the labels are, you could easily distinguish them by their label, right? Like this. So I have distinguished them using different colors. So this wasn't the case that you had the labels, right? And that would fall into the supervised learning. But in our case, it's as if we have all in the same color and we have no idea which one belongs to the other, belongs to what group. So we have to find a way in order to gain some information about this data set of D. For instance, in this case, we were trying to group them using their size and their mass. So they would have these characteristics in our graph. So today and the upcoming sessions, we're going to see what are the common techniques in unsupervised learning that we can sort of group them into different set of distinct groups. So one of them, which we discussed today, is clustering. The other one is density estimation, and the third one is dimensionality reduction. One of the well-known examples of this technique is PCA. So today we're going to start with the clustering techniques. All right, so if you want to have a definition for clustering, is as if you want to partition all your data that I showed in the previous slide. So you want to partition your D data into K disjoint clusters. So this is an important factor here, being disjoint. We don't want these partitions to overlap to each other. And of course, your N is obviously much bigger than your K, so the size of your data must be way bigger than your K number of partitions. So we want to do this partitioning such that elements in each cluster are close to one another. So if you draw it in a figure or in a graph shape figure, by distance we mean they're close to each other in their respective dimension, in their respective axis. Okay, so now given our data set of D, we want to output some clusters. We call them S, S1, S2 up to Sk, and K is the number of clusters. So all these Si's are a subset of D, our data set. And also the cluster centers, which we show them by mu. So the vector of mu1 up to mu I, I'm sorry, mu k, because each cluster has one center, and all these centers are also in the dimensional space of R. Sometimes we call these cluster centers centroids, so you might see it in other texts. Sometimes they call it centroids. So, as I stress on the fact that they should be disjoint, so we have two simple conditions for these clusters. First of all, they should be disjoint, so there should be no overlap between each of the I and j's. And secondly, the union of all these clusters must represent our data set D, right? So you have, if you have this set of data and you cluster them into two, so K was 2, so S1 and S2, these two must not overlap, so this is wrong here, so you don't have to overlap here, first of all. And then if you had a data remaining here, you should find a way to fit it into one of the clusters, because these two, the union of all, should represent all your data. All right, so going forward to make these clusters, how are we going to calculate the error associated with that? So in order to approximate the error for cluster Sj, we need to actually sum all the EJs, so we call it approximation error, over all the clusters Sj's, and that's going to be the norm of each of the Xi's minus their centroids, or the center clusters. So each of the data within that cluster, suppose you had this set of data in a single cluster, and this point was your center point, we call them mu. So in order to calculate this, you have to calculate the distance between every individual x's with your center point, right? So now given D, so all your data set, we need to define a way to calculate the in-sample error of S, all the S's. So that was only for one case you saw here. So you have many S's, K S's, and naturally K center points, right? All right, and that would be just a summation of all your EJs. So if you expand this, you're gonna have now you can use a function of mu of xn to generalize this, so for all the clusters. So in order to find the approximation error for our clustering, so we need to calculate, so suppose you had these many clusters of your data, and each of them had its own mu, which was the center cluster. So for each case, you have to find the distance between the center cluster and from the data, each of their own respective data, and then that would be the summation of all. Okay. Yeah.
So do you consider the center to be the target where you want the points to be? Is that why you're calculating the distance between the center?
We don't want our points to be in a center. I mean, if so, yeah, that's a good question. If ideally, if all of the points were all aggregated in one point, so if instead of this and this center point, which was mu, if you had such a data like this, and all those 10s were like exactly there, yeah, our center point was this as well, and that would be the ideal case. But in a real world problems, normally this brilliant situation won't happen, right? Because you have a distribution of data, and you want to make sure that you have enough of clusters that represents that data, and also you want to make sure the centroid are representing that cluster with a minimum, approximation error. So these two should hold. So later on, we're going to see a well-known technique called K-mean clustering that is going to go iteratively and find more clusters and find their center point of that clusters. All right. Okay. So now, given this number of clusters, so S1 up to K, so we have K clusters and K center point. We want to calculate the error. So mu xn, as I mentioned, it's going to be called the center of cluster to which this xn belong to. So if you want to formalize it, in general, we would like to minimize this error for all the clusters. And sometimes during this process, we notice that why not add another cluster, right? So in this case, we have two clusters. K was 2, and we had 2 mu. Why not? At some point, we're going to see that, okay, we wanted, for the cluster 1, we could have 2 clusters like this, and that would be 2. And this turns our problem with 2 clusters, K2 towards K3 here.
So what's the point of having like those 2 clusters instead of the cluster?
So actually, there are 2. I should have drawn them better. So these are 2 disjoint clusters because we don't have any data here. And so now this is not a cluster anymore. So this is actually your S1. This would be your S2. And in this case, it would be your S3. So
you had 2 clusters originally.
That's right. So it turned out that if we break these clusters into 2, like this, we would have this minimization in a better place, right? So yeah, actually, if you want to call it better, it's going to be, this one would be S1, this one would be S2, and this one would be S3. So now the application of clustering is very, very common in many of the domains of, I would say, data science. Whenever you have data and you don't have any label for those data, you want to be able to categorize them, cluster them, group them in a way that you can understand better information from those. And here I'm just bringing 2 more well-known actually applications. So first one is the topic discovery. So suppose you have So suppose you're facing with many documents, text documents, and you want to cluster them into K groups where documents belonging to the same group have similar topics, right? So this is a huge problem. If you want to if you want to import your old literature from a library and you scan those documents, and through OCR technique, you're going to learn the text out of those scanned documents. So you have a bunch of text in documents. It's like millions and millions of pages. So you don't want to read all pages individually and understand what was happening here in like 16th century. This one belongs to that one. So if you want to generate an index out of those documents, so clustering would be a good technique. You have n documents. You want to cluster them into K groups. So how are we going to do that? In this case, we have to define the x's and mo's, right? So what would the x's are? So the xi's would be equivalent to the histogram of the words in document I. So for instance, you're going to say that, so if you know histogram was showing the number of repetition of certain words, so like, I don't know, the word machine would like happened this many times, like 2 million times, and the rest of the words were like, I don't know, that would be like, I don't know, car, no, that wouldn't be a car, that horses or whatever. So you want to be able to cluster them using the histogram of the words. And what would be your moves are? So the moves would be histogram of word in group J, used for identifying that topic. Right? Does that make sense? If you wanted to have a more in-depth definition of the histograms and the distributions, you can refer to the Boyd in chapter 4 in your references. But that would be one very useful, use case for that. Also, on the second use case, I brought the recommendation systems that you already got to know with. So also in recommendation systems, mostly in say music, like in Spotify, you can apply the same technique for the number of times each user was playing certain songs. If you see Spotify, they have a histogram on the right side, and it's going to show the amount of time. So like that would be the music number 1. And normally in Spotify you have a meter here, and the more frequent it was played, it was shown here. And when you hover on your mouse, it would say just this one has been played like 1,500 times. And the more it goes higher, it's going to go higher. So on that case, so on the recommendation systems, we want to cluster consumers based on common preferences. And based on those common preferences, we want to provide recommendations. So let's define xi's and mui's here. So xi would be a vector denoting the number of times user I has streamed each song in a music library, right? And corresponding to that, the muj's would be the average number of times users in cluster J have streamed each song in the library. So through that, you can find common preferences for many users, and you can recommend the same taste of music for a new user that had, expressed similar attributes towards certain songs. Now let's go back to the coin clustering problem that I brought up at the first of the session. You were right? Yeah. No. Okay. So now going back to those coins. So if you were to classify them, it would just be like cluster D into K groups. So the first part would be clustering, and then label each group by hand, right? If you knew the labels. But now you're facing only clustering, you don't have any labels. So how are we going to gain some information about the coins? If you recall the first or second session, I was talking about like you have sort of a vending machine or ATM-like machine, and it accepts coin. So inside that, it has a measuring device that measures both the size and the weight of the coins that are getting inserted into the machine. So with two, now we have two features, and we can sort of plot them in x1 and x2, where x1 pertains to size and x2 represents the weights, right? And that would be the case for classification. So say we didn't have this. So it would turn. That would be the case that we had the labels. But here we're not. So what we do here is gaining information from the size and the mass or the weight, and sort of find a way in order to cluster them into groups. Like we could, divide them into 4 groups or 3 groups. At some point, it would be messy. At here, like we didn't know which this data was belonging to which group. So you might consider this one as a whole one cluster, and sometimes you want to consider it into 2 smaller clusters. So, and these 2 ways would define 2 different set of EIN for us, right? The approximation error would be different. So now we're going to see how we're going to do that when we have no labels here. So in the perfect world, if you wanted to cluster them in the optimal way, we should have done this clustering technique for all individual data sets, data within our data set. And this problem would yield, the optimal clustering would yield as an NP-hard problem. So if you're familiar with the complexity of the problems, NP-hard is considered as one of the hardest classes of problems. So this would be NP-hard without overlap with NP problems. I mean, have you thought about this in your courses, the complexity of the problems, sort of? Yeah. So yeah, and you would have like NP complete here, but NP hard is considered as the hardest complexity within the NP classes. So you see that NP, the optimal clustering is a computationally intensive task to do. So what instead we can do is using some heuristics. And the most well-known heuristic defined by Lloyd, so this is double L, OYD, in 1956, so like 6 years ago, as k-mean clustering. So in this case, using the weight and the size, we would be able to sort of group them into 3 groups, like 1 cents, a quarter, tens, and so on and so forth. So before introducing k-mean clustering, let's discuss about 2 problems within this process. First, how can we minimize the overall approximation error? So let's talk about this. All right. So now we have k clusters S1 up to Sk, and we want to be able to find the center point of these clusters, defined as mu1 up to mu k, to minimize the overall ensample error. So En was the summation of all j's from 1 to k, ej's. So ej was representing the approximation error for each of those clusters, right? So if you expand this, we are interested in minimizing this equation. So if you see this, because you are summing up the differences between each of your x's from the center point within that specific cluster of j, so you see that Sj, within each of those Sj's, this equation only depends on its own Sj, right? And not on all the other Sj's. It's like we are making a summation for all the clusters. So if you add these clusters, when you're dealing with this cluster, you don't care about the other 2, right? When you deal with this cluster, you don't care about these 2, right? So that's why this equation only depends on Sj and not on all the rest of the S1, S2, Sj minus 1, Sj plus 1, and the last one. So only this. So now, yeah, as an example, if k was 2, you add these 2 clusters. So it's as if you want to minimize the Ej of mu j for all the moves in 3-dimensional space of R, and you want to have this summation Yep.
So the last word's supposed to be S J. Third line only depends on S J.
Yeah, this is only dependent on S. Yeah, and that's why you don't have SJ here.
No, I mean, yeah, like that last word just says JN. What is that? On the very right.
All right, yeah, maybe this is SK. Yeah, it should be SK, thanks. Yeah, I'll fix it when I upload the slides. Okay, now when we simplify this, we're gonna come up with this equation. So for mu j, if you want to calculate each of those mu j's, it's as if you compute 1 over the size of sj, and then you multiply that with the summation of xi's within that sj with xn. So as I mentioned, sometimes they call it centroid. So it's going to be the centroid on sj. So in order to find the optimal solution for that, you have to find the gradients of ej of mu j, and we equal them to 0 to find the solution for this equation, right? All right, expanding this is the gradient of mu j sigma xn in sj, and that would be the formula we use. So you can change this too, because the gradient of summation would be equal to summation of gradients. So and then we want to simplify this in the next slide. So okay, now we arrive to the point that we have a summation of xn within sj, and we want to compute the distance between each of those xn's with their own corresponding mu j. So expanding that, so xn minus mu j, the raise of 2. So xn minus mu j, the raise of 2 would be this. First one raised to the 2, second one square, and since you have minus here, you're going to have this minus 2 of the first and the second component, right? So now you have a summation of xn's within sj, the first component raised to the 2, the second one raised to 2, and then minus 2 of this. So since we are making the gradient, so we want to calculate the derivatives with respect to mu j. In this case, because this component doesn't have any of the variables we are interested in, so it's going to be equal to 0, right? Because it's a constant in this case. The only thing that we are interested in getting the gradients is this, which had the mu here, and also this one, and that would be the coefficient for that, right? So getting the gradient, this was 0, this was considered as constant for us. This comes back here, that would be your 2 of mu j's, and this one, because it had the first order, it's going to go to 1, so you have only 2 xn's, right? So that would be the answer. Now you just have to solve this, and you find that mu j multiply the summations is going to give you an indicator function. So if you remember, the indicator function was telling you if it's 1, go 1, if it's 0, go 0. So you just pass the true value. And finally, you're going to come up with this formula that we mentioned in the last slide. So the optimal solution for that specific mu j is 1 divided by sj, the size, multiply the summation of x n's within those sj, right? So now we can understand how we're going to, given a set of clusters, how we're going to find their center point. So now, at least we know we can solve half of the problem. If we know the clusters, we can find their center points. So now let's see how many clusters we can find. All right. So now let's go for the second problem. So now, given all these moves that we found, find the s's to minimize the in-sample error, right? So it's the other way around. It's the other complementary part of the question. So given xi's within our data set, which cluster should be associated that xi with, right? Does anyone have any intuitive answer for that? So suppose you have these clusters, and a new data point comes, and it's like here. Intuitively, which cluster I should assign this to? Why? Right, exactly. So in a simple form, you just have to find a cluster that is has the nearest distance, so it's closer to that. But it makes sense to minimize the EIN, right? So now let mu of xi denote the cluster center of xi. So if you expand this, you're going to have it for all those clusters, right? So the first one is 1, is 2, and that would be the ith one, and the last one. And again, take into account that each of them only involved with their own cluster. So for xi, so this is the only term involving the xi within that. So if you want to find the optimal solution for that, then the move of xi, so that we find which of these clusters the xi should belong to, is just a matter of finding the minimization problem of that for all the moves. And intuitively, as your colleague suggested, so we have to assign xi to the nearest cluster then, right? All right, now we have all the foundation of building our simple algorithm, which was called K-mean clustering, because we know if you have, yeah.
So is that the left not squared?
Which line?
Xn minus Uxn?
Yeah, that's right. Yeah, this is xn.
Is there an exponent?
Oh yeah, right, that's right. Good, I'll fix that as well. All right, so now we have all the foundation of building our K-mean clustering. If we have certain clusters, we know what to place we know how to minimize the error for our moves. And if we have the moves and clusters, and we have a new data, we can add it to the nearest cluster, right? To do the dual problem of these two. So now let's just define the algorithm here. So first, we have a data set which we don't know the labels, so we just initialize k clusters, and k is the input by the user. So when you use k-mean algorithm, normally you can define the number of k to start with, and it's going to come up with the answer. So say you want to use MATLAB or Python or I don't know, a C implementation, so you're going to pass the k, and it's going to initialize those moves in a random fashion. So move 1 up to move k, right? And then it's going to construct the S's, the clusters, k clusters that was asked by solving the problem number 2 that we just saw. So the closer x to each cluster belongs to that specific cluster, right? After it constructed that, it's going to update the moves that was initialized randomly at first. How are we going to do that? We just saw it in the problem number 1. And then simple enough, we just have to repeat the step 2 and 3, these 2 steps until we converge to the minimal approximation error or our optimal point. So as you see, it's pretty intuitive and simple. And as you can imagine, it's because it's a heuristic, it doesn't give you sometimes the optimal solution, because depending on the number of clusters you choose, you won't be able to find the global optimal. So that's why as the properties of K-mean clustering, you can mention that it's locally optimal. It's not globally optimal. That's why it might not or will not find the optimal partitions in general, right? So this is partition for partition in general. Okay. Any questions? Okay, good. So on Friday, we're going to start with density estimation and other unsupervised learning, and you have your midterm in the evening.